Tell you what, you do this, I'll do the next one. So what is a statistic? Yeah, so the statistic is a number that describes the sample. Do we have a number describing our sample here? So that describes the sample size. So you're right, that does describe the sample. Anything else describing the sample? Yeah, fantastic, good. 79% of those polled believe nurses have very high or high honesty and ethical standards. Now, parameter, we don't typically know. And in this case, we don't know the specific value for the parameter. So when we want to describe the parameter, we're just describing what it means. So if the statistic is the 79% that believe nurses have high or very high ethical standards, then the parameter is the value describing the population, right? So maybe we could say whatever proportion of all US adults believe nurses have high or very high ethical standards. Are those okay so far? You're even nodding quietly. All right, so let's look at E. Describe the given confidence interval. So what number there involves the confidence interval? A couple of numbers, actually, a few numbers even. Yes, Connor. Yes, plus or minus 4 percentage points. That's called our margin of error, right? And what are we adding and subtracting that 4% to? Close. The 95% is something we're going to talk about a ton in the second half of the semester. Right now, we just know it gives us the level of confidence. Instead, we're going to talk about the 79% because we know a sample probably isn't going to match the population exactly, right? There's variation between random samples. And so we think it's going to be probably close to 79%. And what this does is give us a range of reasonable values. So if I wanted to write this as an interval, it's going to have a lower number and an upper number. What is that lower number going to be? Yeah, 75. Where did that come from, Tyler? 79 minus 4. Perfect. And then what's the upper number going to be? It's going to be what? 83. Perfect. Wait. Yeah, 83. I'm just not as good at adding. And so again, we're going to talk about the interpretation of that a lot after midterm. Right now, we just want to think of that as a reasonable range of values for a parameter. Okay, so one other thing we talk about are design, inference, description. And so really quick, just to review those words, what up here is describing and what up here, where is the inference coming into play? Just one of them even. Yeah. So that's what we're talking about. Yeah, you're right. So I guess, what are we describing and what are we making an inference about? And this is going to be true of pretty much all the problems we talk about. We're describing our sample, right? We know our sample had 79% of people who believe this about nurses. Do we know the value for our population? We don't. We think reasonably could be between 75 and 83%, right? That's a range of reasonable values for us. That's an inference we're making based on our sample. If we have a good representative sample, our population looks the same, and so we wouldn't be surprised to find the value in that interval. Does that make sense? The difference between description and inference? Okay, so let's ask Lizeth, anything to add? Okay. Yes, question. Is that Lou? We got 83% from adding the 4, and it looks like a 2 because I write like a child. Good? Yeah, the last one was just out loud, but yeah. Oh. All right, then we are moving on to chapter 2. So remember, chapter 1 was just a big picture chapter about all the stuff we're going to talk about. Chapter 2, there's a ton of graphs and charts and math. So here, I found a table of values for gestation periods for different animals, and I graphed it right here. What type of graph is that? It is a histogram, yes. And I think some people might think it is a bar chart. How do we know it's not a bar chart? Because they look a lot alike.
I heard somebody say it.
Yeah? You probably have the right answer. So visually, that is one way to look at it. Bar charts, we typically don't. We typically have gaps between the bars. Here, a gap is meaningful. It means there's 0 values in there, right? And so there is a difference there. What type of variable is this? We talk about quantitative and categorical variables. What type of variable is gestation? Yeah, it's quantitative, right? And bar charts are for categorical variables. Histograms are for quantitative variables. Okay, good. So we want to describe the shape of this distribution. Typically, when we're describing shape, we describe symmetry, mode, skew. So what would we say about the mode of this? Well, I see one peak, so I'm going to call that unimodal. And is it symmetric? Is it skewed? It is skewed in a direction, and that is typically the tricky part, because for half of us, left and right makes sense the way it is, and the other half of us, it seems like it should be opposite. For me, I'm in the camp that it doesn't make sense right away. I like the terms left tail and right tail. It makes it easier for me to understand. And what I do is, if you pretend you're drawing a dinosaur around it, it'd be, where's the tail? So that's right-tailed or right-skewed. So this might be tough to remember. We often hear median and mean, and sometimes one is better than the other. So if you remember, for a symmetric distribution, they're all the same. When we have a skewed distribution, one of these measures of center is going to be better for us to use. Mean or median is more appropriate when we have a skewed distribution. Okay. Median, that's a very good answer. Because what? Well, so we do want to be careful about saying the middle, because when we, the problem with language is it's so ambiguous, right? And so we want to use certain words very specifically. And so when we're talking about mean, median, mode, those are different ways to measure the middle or center, right? And so we probably don't want to use that word, but I think I get what you're saying. So you remember the words sensitive and resistant? One of them is sensitive to extreme values and the other is resistant to extreme values, right? And so which one is sensitive to extreme values? It gets pulled in the direction of the skew. The mean does. That's absolutely right. And if you think about how they're calculated, the mean includes every value point. Of course, if you tack on a really big number at the end, it's going to make the mean much bigger. But for the median, it's not going to change much. So median, because the distribution is skewed right, or you could just say skewed realistically, and the median is resistant. Now, C is not that different of a question. It's asking the same type of thing, but asking about spread. So, we talk about range, standard deviation, IQR. And if I'm not using the mean, that immediately tells me I'm not using one of those. Which one? The what? Yes, why? Very good. Oh, IQR doesn't actually use the median. It's our third quartile minus our first quartile. But I know what you're saying, right? It's part of that 5-number summary that goes with the median. That's perfect. You're right. We don't use the standard deviation. And if you think back to the formula for the standard deviation, it involves the mean, right? And so if the mean's sensitive to extreme values, the standard deviation also will be. So for part C, going to
Stickies.
Yeah, I
think so.
Okay, I'm kind of impressed that I was able to do that on my own. Oh, but it's not covering it up. Okay, so I just, nope.
So you can either grab that and draw a box with your pen and then delete it. That's usually the easiest.
Okay,
And then tap. Delete. There you go.
okay. So, what are we doing? Part C. C. Nope.
Gotta go back to your pen.
Gosh. IQR. And again, you could say something like, because the distribution is skewed and the median is resistant. Now, what type of distribution, when are we going to use the mean? Involving that, what is the distribution going to look like when we're using the mean? Yeah, definitely for bell curves. These nice symmetric curves, mean, median, and mode for a bell curve are all the same. We're going to end up using the mean, and that describes like the second half of the entire semester. So right now we're talking about using the median a lot. Later on, we will talk more about the mean. I mean, we use the mean all the time anyway. So good. Now, do we feel okay on this? No. Okay, so why not? I mean, there are fewer of you than usual, so this is really easy to get a quick answer. Do Lizeth? We'll ask her. Is it just, does it make sense? Lizeth, will you explain what's going on? Oh, there's a microphone over here. Well, talk loud so the people over here can hear you.
Is it the mean or the median? And then the median is resistant, meaning that it can't be pulled to the left or the right. So the median essentially stays in the center, while the mean can be pulled. So in this case, the mean is pulled to the left, making it right skew.
She's Italian like me. She has to talk with her hands.
I'm like, is there anything specific?
Okay, you know what? I got an idea. Well, let's see if I can do this. If I do another note, will it go on top of that and make it disappear? Hang on, I'll just move it.
Yeah, there you go.
Okay. So let's do this. 1, 1, 2, 3, 3. What is the mean of that? How do we find it? Yeah, how? Yeah, fantastic. So what is it? Okay. And then what do we do? Okay. So yeah, the mean's 2. All right, what's the median? Well, there's 5 numbers, right? What do you get if you divide 5 by 2? Just, roughly. 2.5, right? So 2 on each side. Our median is 2. They're the same, right? Because it's symmetric. They should be the same. Now, let's say I add an extreme value. 1, 1, 2, 3, 3, 1,000. So it's almost the same. All I did was add 1 number, right? What direction is this skewed in? So typically when we talk about numbers, when we're saying left and right, when we write numbers, we usually write smaller numbers on the left and bigger numbers on the right. So when we say skewed right, we mean skewed towards larger numbers. When we say skewed towards the left, we mean skewed towards smaller numbers. And so we make this really big jump all the way over to 1,000. That's where the tail is. And so this would be skewed to the right, which is that what you said? I think it maybe. So what's the median? How many numbers are there now? 6. All right, what's 6 divided by 2? Okay, so 3, 3. So the middle now, and I just said that word I said we should be careful about, is directly in between those. What's exactly halfway between 2 and 3? Yeah, how do you figure that out if it's a weird set of numbers? Absolutely right. You find the midpoint atom and divide by 2, and you're right, 2.5. Now, the mean, without calculating it, is the mean going to change much? A lot or a little? Why? Because you're adding on that huge number and you're only dividing by 1 more, right? Does anybody want to calculate that? Because I don't want to bring out the calculator. We just add them and we divide by 6, and it's going to be... All right, I'm just going to write 167.8. Now, of those 2, which seems more representative of the center of that data set? Median, right? So does that make a little bit more sense? Okay, good. Is the mean larger or smaller than the median? So going back here, which one's larger? The mean or the median? Which one gets pulled in the direction of the skew? More. The mean, right? And it's exactly the same as this one. This is skewed right. This is skewed right. This isn't as drastically skewed right. Yeah, so the mean is larger. Since the distribution is skewed right. Now, for the 5-number summaries, if we have time a little later, I'll show you how to do that by hand. I want to show you how to do it in the calculator too. So let's see if I can do that. Nope, that's not the right button. How do I get the calculator back? Okay, fantastic. So if we want to find things like the mean, median, mode, standard deviation, quartiles, our calculator can help us by going to STA, edit. And if you have stuff there, you can go to the top and clear it. Oop. This is a fake app for a calculator, so I'm hitting the delete button. You want to hit clear on the real calculator. All right, so I put in my numbers, which if you look at the table are right here. 365 days, just like, well, a year. Bayer 220. And I would strongly encourage you to do this with us, because if it goes wrong, I can help you. YZF can help you, and we'll figure out what's going wrong. Oh. Oh, so the nurse study that I was talking about earlier, nurses are almost always at the top of the list. Apparently, after 9/11, firefighters were 1 year. Otherwise, it's been nurses at the top every year. Any guess what the lowest on the list is for professions, people not having a high or very high opinion of their ethics and honesty? Yeah. Used car sales. Yeah, that's at the bottom. And there's another one that's right there with it. Congress. Yeah. Yeah, nailed it. First 2 guesses got it. All right, so hopefully I got all the numbers. I honestly don't know if I did. Hopefully you would yell at me if I did. So once they're typed in, what do? We go to stat again, very good. And we go over to calc. And this time I'm going to go to one variable statistics. Oh no, I'm getting an advertisement.
Just kill it.
And I hit enter and it gives it a bunch of stuff. Now, if we're looking at the top, that X bar, what does that mean? Mean, okay. S is our standard deviation for the sample. N's our sample size. Hopefully that's actually 20 things. Minimum, quartile 1, median, quartile 3, and the maximum. So are you all getting the same numbers as me? Really? Everything's the same but Q3. I'm missing a number. Okay, fantastic. Stat. Edit. All right, can anybody spot what I'm missing? 280. 280. We got it now? Yeah? Great. So if you are not getting these numbers, raise your hand and one of us will come help you. You can do that on the computer too. Everybody's getting it? Okay. Anybody on the computer?
All good.
All right. So it says find the 5-number summary. I haven't actually written that out yet. I'm gonna erase this. Is there a better way?
Yeah, I usually just grab the lasso
Oh, okay.
and lasso everything with the pen.
I see.
Yeah. And then tap in the box and then delete at the end.
Okay.
There you go.
So 5-number summary consists of the minimum. Oh, so it's Q0, Q1, Q2, Q3, and Q4, which we don't always use these terms, but we break it into quartiles. This is how the quartiles are broken up. Usually we call this the minimum. Usually we call this the median. And usually we call this the maximum. So the minimum is 22. That's the easy one to find. It's just the smallest number. You don't need a calculator for that. The maximum is, what's the maximum? 624. Median is 115. Q1 is 50.5. And Q3 is 244.5. So when we talk about the 5-number summary, we are talking about the quartiles, or minimum, Q1, median, Q3, and maximum. Are there any potential outliers? Okay, so outliers can be a little ambiguous in what it means sometimes, but we have a couple of good meanings for it in this chapter. And that is that it goes below 1.5 times the IQR below Q1, or 1.5 times the IQR above Q3, or it's more than 3 standard deviations from the mean. So what we're going to do, since we're talking about quartiles, is we're going to use the IQR to decide if there are any outliers. Does it look like there are any outliers? Maybe what? What animal? Yeah, maybe the elephant, right? The one way over here. So what I'm going to do is write down my IQR. That is equal to Q3 minus Q1, which is 244.5 minus 50.5. So that is 194. Okay, so I said that would be below Q1 by that amount. So Q1 is equal to, I erased it, but it's 50.5. If I take 50.5 and subtract 194 from it, I don't even need to look at what that value is because it's very negative, right? And do we have any negative days? So there are no outliers on the lower end of things, which we didn't expect that looking at the graph. So if I'm looking here at Q3, which is 244.5, this is where we suspect there might be one. If I take 244.5 and I add 194 to it, oh, no. We get 438.5. Sometimes people call these the lower fence and the upper fence, and anything beyond this is an outlier. So do we have any numbers that are bigger than 438.5? We do. It's the elephant, just like you thought. Okay, so that is an outlier. So are there any potential outliers? The elephant. Any other ones? Nope, that's the only one that went past 438.5. Sketch a box plot. Okay, so the box plot is just a way to graphically display the 5-number summary and include information about outliers. So what we do is we make a box around Q1 to Q3. Now I need a scale on here. The smallest number of days was what, 22? Well, I guess I could just look at the 5-number summary, 22, and the max was 624. So I need a scale that includes both of those on there. Now I'm just drawing it by hand, so it doesn't need to be super nice. I'm going to do this. I'm going to go by, I guess, 100s. So 0, 100, 200, 300. Okay, now my Q1 was 50.5, so that's going to be right around here. My Q3 was 244.5, so that's right around here. It's my box, and I divide that with the median, which is 115, so right around there. And then I draw a line out to the minimum, which is 22, so here-ish. I draw a star for any outlier, which, where is the elephant? It was 624, so I'm putting that in the wrong place. Let's just do that. So maybe here. And then I draw a line out to the next highest point, which was, what's the next biggest one after elephant? What is that? Okay, I thought you might say the animal. 365. There we go. Would a pie chart be an effective graph in this context? What do we think? Why not? No. Internet people?
They're not talking.
Because there's just too many the graph, the pie chart would be messy. You don't really want values.
Oh, when there are a lot of categories for a pie chart, it can be a poor choice of graphs. That's not the issue here, though.
How about too many variables?
Too many variables. So I think that's similar to what Michaela is saying. It's that can be a poor choice of pie chart, but it's not the issue here. Related. Yes, pie charts and bar plots or bar charts are for categorical variables. This is a quantitative variable, so a pie chart is not possible. Can I move on? Are we okay? All right. So then I have a pie chart because we keep talking about them. I just picked one of my classes and found what class standing each person had in it, and I made a quick pie chart. And it looks like, what is the modal category? Yeah, second year.
Do you need the calculator?
Oh no, I won't need that again for ages. Nope, that's not it. Like this.
There we go.
Oh, even better. So I mean, we just look at it, right? We see the biggest section. That's one of the great things about pie charts. And to Michaela's point, and whoever said it on the internet earlier, Andrew, when you have a lot of different categories, this can look kind of like a mess, right? If there are too many things in a category. 4 is easy. So how many students in the class are first years? How would I figure that out? So how did you do that?
So you go here. And then you have to pull it up and then you have to drag it. Oop.
Anybody know? Well, we do need the fact that there are 94 students in the class. And I ask about first years. What percentage of students in the class are first years? 18.1. So how would you turn that percentage into account. Yes. Yeah, that's exactly right. You would say 0.181, the percent is a decimal, times the total, 94. So 17 students. Now, it really said 17.014 students. Why do you think that happened? Why wouldn't it tell me the actual number? If I base this on a real class, I shouldn't be getting a decimal. That's true. So that's definitely why I rounded, but why is the calculator lying to me? If we add all of these up, what do we expect them to be? 100%. Now, if it's a little bit off, we might not be too surprised. So how much off might we expect it to be? What can mess up the numbers? Rounding, right? And so I've rounded to 1 decimal place, so I wouldn't be surprised by an error that's 1 or 2 decimal places, right? And so that's why that's happening. Sketch a frequency Pareto chart of the distribution. And the reason I said Pareto is because I figure a lot of us forget what that means because it's just kind of briefly mentioned. So a Pareto chart is a specific, well, what other kind of graph do we use with categorical variables? Yeah, so that's what we're going to do. Does anybody remember specifically what Pareto means with the bar charts? Just yes, in order, right? So usually we go from a descending order. So it would help if I knew, because it says frequency instead of relative frequency, the percents, if I knew the counts. And so we said this is 17. So we need to find the other ones. So go ahead and try to find the other numbers.
You want to zoom in on that?
Oh, sure. That's
There you go.
much better.
Awesome.
Oh, we got an answer.
That was to that question.
Oh, okay.
Yeah.
So I already messed it up. I was putting them in order from first to 4th year, but we really want to put what first? What's the largest? Well, we already said the modal category, 2nd year, so 2nd year. And the second largest is 3rd year. And then we have 1st year and 4th year. And the smallest number, we go from 12 to 41. So I'm just going to go by tens here. Second years, we have 41, so a little higher. Third years, we have 24. First year's 17. And fourth year's 12. Does that make sense? Lizeth, you want to get on the microphone again? Just for fun. Do you have anything to say? Okay. Okay, good. So we'll keep going. Now, this is data that I just took from some website. It's probably made up. It's back-to-back stem plot, shows pulse rates for 19 students before and after light exercise. And so really what I wanted to get at here is, can you read a stem plot or even a back-to-back stem plot and give us a little more practice on describing distributions? What is the smallest value in the before data? So what is the smallest value here? 0 is actually not. Oh, okay. I see what you're saying when you're reading the stem. So we want to look at is just a stem plot where this is our stem and these are our leaves. And this is a separate stem plot to the right where you can't see where I'm moving my pencil. So I should probably do a better job of that. This is the stem. And these are the leaves for after. Instead of drawing the same thing twice, we just drew the leaves for the before on the left side. So remember, if I want to read this 8 here, that's 118. We tack it onto the stem. If I want to read this 0 here, this 0 right here, that's for 100. So when we're reading this, what do we think the smallest value in the before data set is? It's going to be what? So remember, we're attaching the stem to each one. So for instance, this number right here would correspond to 110. It would be 68. Okay, right here, 68. It goes out to 69. Our biggest number in the before is 110. So 68. What is the range of the after data? So does anybody remember how we calculate range? Yes, good. So 68 was, yes, that was perfect for that one. Maybe that is the range. How do we find range? Nobody remembers? Someone remembers? Perfect. Maximum minus minimum. Very good. So we are talking about the after data. So for part B, maximum minus minimum. So you have to read two different values, and we're looking at the after here. Oh, that's good. So what is the maximum value in the after table? Okay, I saw someone mouth it, so we're going to go with it. 146. What is the minimum in the after? And you know what? I'm just going to hide this. Let's just pretend we're looking at this stem plot right here. 86, perfect, minus 86. So the range, 146 minus 86 is 60. Oh, and that was the answer we got online a minute ago. So great work. Mm-hmm. Yes. Yeah. So if there was a 0 over here, so if there was a 0 here, that would correspond to 60. But because it's blank, there's nothing there. Thank you for asking that. I bet a lot of people were confused by that. So it actually is coming from the 86 right here. So C.
Do you have a question?
Yes. I'm sorry? Yeah, so maybe I was reaching too much with this example. In the class, we typically only talk about these single-sided stem plots, and I just wanted to have an extra example in there. So you just flip it. It's the same as if I had this, if I marked this out, and it would be the same as 6, 8, 8, 8. So I could write. So if I wanted to take this and write it on the right, like we typically do, I could say 6, 8, 8, 8, 9, 7, 0, 1, 1, 4, 6, 6, 8. Does that make sense? So it's just a way to display them both at the same time. You don't actually need to worry about that. I just wanted to have two examples in there, and maybe that was a bad choice for me. That makes sense now, though. That's what matters. Thank you for asking. So, what types of other graphs would be appropriate to display this data? So scatter plots, you know what? Because there's two quantitative values, scatter plots are for bivariate data. So you're exactly right. That's a much better answer than what I was thinking of. I was thinking of when we're only looking at before or we're only looking at after. But your answer is way better. So in other words, what other graphs are for quantitative data? Histogram, yep. Dot plot. Now, if we were using both values, a scatter plot might not be crazy. And so Lindsay had a very good answer when we have bivariate quantitative data. That's very good. I want to come back to this if we have time. I don't think we will, and show you how to find the median and the quartiles by hand. So I'm going to jump ahead to make sure we talk a little bit about the empirical rule and regression. Now, the empirical rule, some people call that the 68, 95, 99.7 rule because it, tells you those values. I've broken it down here with the individual sides using symmetry. Okay, so who's in a biology related major? What does MMHG stand for? Milligrams of
Millimeters.
millimeters of mercury. Fantastic, because I just took this from a question software. Millimeters of mercury. Fantastic. So when we look at this, it's always a good idea to draw a picture. Just draw a nice normal curve, a nice bell-shaped curve. And right in the middle is the mean. And the median and the mode, but we're looking at the mean right now, which is 120 mmHg or millimeters of mercury, which I knew all along. So what we want to do is divide this up using standard deviations. And so let's see, standard deviation is 12. So if I go 120 plus 12, that's going to put me at 132. And if I subtract 12, that's going to put me at 108. And if I add another standard deviation, 132 plus 12 is 144. And 108 minus 12 is 96. Okay. And we could go out another standard deviation, but for the problems I've written down, this is going to get us through. So if I want to know between 108 and 132, that's right here. How many standard deviations is that? One to each side. So the empirical rule tells us 68%. Okay. And so when we ask what percentage of 18-year-old women have a systolic blood pressure between 108 and 132, it's about 68%. All right. So see if you can figure out part B. Anybody got an idea? Yeah, 95%. Perfect. 95% because that's 2 standard deviations. So 95% of 18-year-old women will have a systolic blood pressure between 96 and 144. That is perfect. So then the next two might be a little trickier. And if we want to graph that, I have that. Oh. So the next two, we have to think a little bit more than just applying the rule. It's a little more like a puzzle. Oh, I thought I deleted that.
There you go. When you switch between tools, it deletes the last one only.
All right, so between 10 or below 108, so that's right here. We said 120 is right here in the middle, 108 is right here. So a picture really helps us right away know if we get a silly answer sometimes. What if I said below 120? That's a really quick one. What's the answer for below 120? 50%, because it's right, it divides it in half, right? That's the median, so 50%. It's not asking about that, but that would be the answer. So we know our answer should be more or less than 50%. Yeah, less than 50%, right? So does anybody know the answer? You have it, yes. What is it? I don't have any idea. Probably. So what I would do is I would say, okay, well, I know the middle 68% is right here, right? And so I keep pointing at it as if you can see what I'm saying. So the empirical rule is talking about this portion. Now, I don't want that. I want outside of that. How much is outside of 68%? It adds up to be 100, so 32. What portion of it is over to the left? Half, because it's a symmetric curve. So if I do 32 divided by 2, that's going to give me my answer of 16%.
I don't like the way he did it.
Yeah, Andrew, that's perfect. It's more what you're doing is using the picture that's there and adding them up based on what you see there. And that is very good. You might be wondering why you're getting a different answer than me. So the person online, Andrew, what they did is they said, well, I can just add that 13.5 and that 2.35. And that seems very reasonable to me. I wouldn't do it right away because you won't have this table. So unless you can recreate it on your own, I usually think of the 68, 95, 99.7 because it's less for me to remember. But if you want to sketch out the whole table, you can. But why would that be a different answer than what I'm getting? It's because this one doesn't have written what's remaining over there, right? And so that little extra bit, if we go outside of 99.7, that's 0.3%. And so on each half of that, it's going to be half of 0.3%. So 0.15%. And if you add that on, you'll get the same answer as me. So thank you very much for asking that. All right, above 144. I'm going to go ahead and push through on this one. When I do above 144, and my picture is not very nice, but 144 was over here. And so we're talking about that area. And so how many standard deviations out is that? 2, which means this inner part would account for what percentage? 95, right? 68, 95, 99.7. So outside of that 95 is what? 5%, because we get it up to 100. What portion is going to be there? Someone said half because it's a symmetric curve. So what's the answer? Perfect, 2.5%. And you said we could go longer? Okay, so it is 7 if you have to go, but I'm going to keep going because I want you to know this. All right, so this is Minitab output. An engineering firm is exploring the relationship between vehicle weight in pounds and gas mileage, miles per gallon. Use the Minitab output below to answer the questions. Is a linear model appropriate here? Why or why not? Yes.
Oh, the recording or the handout?
Oh,
I'll send it
Yeah.
out tomorrow.
so, when I say, is it appropriate, what I'm really saying is, does it meet the conditions? And does anybody remember what conditions are necessary? When we talk about linear modeling, linear regression, correlation, any of those things from chapter 3? 3 things. Can anybody remember one of them? It's what? Yeah, it's got to be approximately linear, right? Straight enough is what the book calls it. Yeah. So it's got to look relatively linear. That does, right? So that's straight enough. So I'm going to say for A, I'm going to say yes, because it's straight enough. What else? Yes, fantastic. No outliers. Very good, Alex. What else? One more. No. No, so we might describe it that way. What type of variables are we talking about? Quantitative variables. So if those conditions are met, then yeah, it's appropriate. Describe the association. Okay, so typically when we're describing an association, we describe trend, direction, and strength. So we've already described the trend. How did we say these are associated? Linear, yeah, so it's approximately linear. Is it a positive or negative association? Good, yes. And is it, I don't know, how would you describe the strength? Strong, moderately strong, you know, somewhere in there. Yeah, I mean, it's the R squared's 75%. So I think that's reasonable. Yeah. So negative, strong, linear association. Another way to describe that is just in words. Heavier cars, what happens with the gas mileage? Heavier cars tend to have lower gas mileage. Yeah, very good. Now, write the equation of the regression line. And typically the output specifically says what the regression equation is. I tried to hide it here, only to realize just now that it's right there. So we're going to pretend it's not there for a second, because we want to be able to read it just from this part of the table too, because pretty much all statistical software packages present it this way. Most of them will also give you the equation, but just to make sure we understand how the output's given here. Now we know it's linear. That's exactly right. So you can use y's and x's, or you can actually write out the variables. I usually use y's and x's, but you know what? I'm going to do it this way here. Mileage equals something times weight. What number is times weight? What is the slope? So that is going to be one of the numbers. That is going to be our intercept. So that would be plus 45.65. And the other value, the coefficient, see how it says coefficient for weight? That's the slope. That's how we figure out our slope, right? It's what's attached to our x. And so that's the 0.000627. Now, I am missing something here. What would I really like in my equation that would make it look nicer? To clarify that we are talking about a sample. Yes, a hat. Very good, Al. Throw a hat on your Y, right? That's just to remind us this doesn't perfectly model reality. This is talking about our sample. It's a statistic, not a parameter. What? Oh, yeah, I looked sideways. My eyes are really bad and I copied the wrong number. Thank you very much. So yeah, this is the coefficient right here, and my eye just went in the wrong direction. I should have noticed that because what's the first thing that should have tipped me off that was wrong? Yeah, it's positive, right? And we know it's negative because we saw the slope there. Very good. Thank you for fixing that. Now part D is a little tricky because that's a terminology one. It says correlation. What does correlation mean? We have a specific letter that represents it. R, that's right. That's our Pearson correlation coefficient. And you know what? Minitab doesn't tell us what R is. How do we figure out what R is based on what we're given? Yes, we have R squared. What's the relationship between R and R squared? When I say it out loud, it's a silly question. So if I have R squared, how do I find R? Square root, absolutely perfect. Yeah. So except, you know, the square root can lie to us, right? Because when we do a square root, we really are only taking a positive value. But R can take a positive or negative value, right? In this context, is R going to be positive or negative? It's going to be negative. How do you know that? Perfect. It's negative slope, so R is also going to be negative. So I just say square root 0.7510 gives me that makes sense? Yes. Yes, that's exactly why. When we take the square root's only going to give us positive values out, so we actually have to think in the greater context. It can be positive or negative, and we need to look at the graph for that. Or the equation. The equation would also tell you it has a negative slope, has a negative slope, has the negative R. Yes. No, so that's just a terminology thing. R is the correlation coefficient. Some people call it Pearson's correlation coefficient. The coefficient of determination is R squared. All right, so I'm going to delete this so I have a little bit more space. All right, so what is the predicted mileage for a car that weighs 2,590 pounds? How do I do that? What? Yes. Now, I did not give you a table of values in this problem. If I did give you a table of values and one of them was 2,590 pounds, would I just go with what the table said? I would not. Remember, because this says predicted, it wants the equation to tell us what it is. So for part E, I would get mileage is equal to negative 0.00522 times that weight, 2,590 plus 45.65. And I put that in a calculator. And I get 32 point, I'm just going to round to one decimal place. You know what? I'm just going to round to 32. It'll make it easier to talk about the next problem. What? Yeah, and mostly I'm just doing that to make it easier to talk with you. So F is talking about the residual for a car that weighs exactly that amount, a Toyota Corolla. So that's actually one of the points on the graph. You notice some are above and some are below. Does anybody remember what a residual does? Yes, it measures the vertical distance between the observed point and the predicted value. You're exactly right. And so the residual here would be the observed minus the predicted. And so what is our observed value? $38 minus, for that same weight, we predicted 32. And so the residual is 6 miles per gallon. What does that mean? Did the Toyota do better or worse than the model predicts? Better. That's exactly right. So the Corolla gets 6 miles per gallon more than the model predicts. And we could think about that in a lot of different ways. One, we know we aren't trying to perfectly match reality. We're trying to get a pretty good fit, right? Some are going to be above and some are going to be below. And for one reason, there's not just one variable involved in a car, right? Weight is significant, but it's not the only thing. Good. One more real quick. We're going to do this in the calculator. So if you want to do regression in the calculator, it's pretty straightforward. You go to stat, edit, and you put your X's in for L1. And these values are real. Actually, you nailed it.
Awesome. Oh,
So you know Mandarin? No.
it had a
Okay.
countdown.
Okay. Oh, that's right. That's why it keeps messing up, because this app. All right. So 1896, 1900. And you know what? This is actually true of almost any sport. When it first starts, people are getting better and better and better, and there's lots of records being broken. And the longer it's around, the more specialized it becomes, the harder it is to do better. Oh. But for a while, you might see a linear pattern. Okay, so once you have your data in, you then hit stat again, calc, and we go down to either option 4 or 8, it doesn't matter. And we get our regression equation. So here, A, I'm going to answer y hat equals 0.022x minus 34.837. And it says interpret the slope. Okay. Are we okay with the calculator? Good. If you did not get r squared and r, Did anyone not get R squared and R? Okay. Okay, if you didn't, what you can do is go to second catalog, go down to the option that says diagnostic on and hit enter twice. And when you run the model again, it'll work. And if you're here, I'll help you with it right at the end. So the slope is what number? Okay, 0.022. And you know what? Before I do any of these, I can't do it unless I look at the graph, right? Because I don't know if it's appropriate to do this. So let's go to second stat plot and turn it on. Oh. I'm going to change my window to look like the data. My smallest year was 1896, so I'm going to say 1890. I went out to 1932, so I'll change my X max to be maybe 1940. I'm going to change my smallest Y. The Y's are they're between, 6, 7. So I'm just going to say, I don't know, 4 to 8. And there we have an approximately linear arrangement of points, no outliers, and quantitative variables. So our conditions are met. And when I do this, I'm going to write my slope as a fraction. What's the easiest number to put on the bottom? 1, right? It's the same thing. Now, I think it's easier to interpret when we attach units. And so remember, it's rise over run. So Y units over X units. So what are the units for our Y variable or our response variable? Yes. So meters. And what are the units for our X variable? Years. Okay. And is this increasing or decreasing? Yeah. So I could say something like, on average, the winning long jump seems to increase by 0.022 meters per year. Now, that was C. No, B. So part C says, would it be reasonable to use this model to predict the winning jump in the next Olympics? Why or why not? Yeah. The next Summer Olympics. Would this be a good predictor? Probably. Yeah. So, I mean, you can see people were jumping further. I mean, not every year, right? But it was a generally upward trend. But at some point, you're never going to get someone that can jump 3 miles, right? So, it's going to level off at some point. And it has started to level off. That linear trend hasn't continued perfectly, right? And so if we added on the data for the additional years, I don't know if it's still progressing linearly. I don't think it is. I think it's actually leveled off. But that's so far in the future. It's probably not going to give us a good value. What do we call that? Extrapolation. Perfect. No, this is extrapolation. We do not know that the trend continues. Now, 1 year out, 2 years out, 3 years out, I think it'd probably be a pretty good predictor. 70 years out? I don't know. 80 years out? I don't think so. Okay. 2 more things and we're going to be through this. I can't even read that. No, this is extrapolation. We don't know that the trend continues. Okay. So I'm going to delete, if that's okay. Are we good? Now we like R squared because it tells us one way to talk about this relationship. Now, R squared here, if we look back at our calculator, is 0.478, which is actually not very high. It's pretty low, actually. There's a lot of things that go into how far someone jumps, right? What we can say here is that 8% of variability or variation in jump length is explained by variation in years. One more quick thing. Are we okay with this? Okay, so let's go back up here. I told you I would do one of finding the 5-number summary without a calculator. And that'll just take a couple of minutes. I'm going to go to this data set because it's already ordered for me. And I don't want to have to rearrange another one. Okay, so let's say we're just looking at the afters. So we go from 86 to 146, right? So the 5-number summary is minimum, Q1, median, Q3, maximum. 2 of those are easy. And I think we've actually already talked about those 2. What's the minimum value in the after list? 86, perfect. And what's the maximum value in the after list? Okay, 146. Now, median, we have to look at how many numbers we're talking about, right? And it said 19 students. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Good. What's 19 divided by 2? It's 9.5. All right, good. So cut it at 9. So if I look at the first 9, 1, 2, 3, and I can write them out. 86, 87, 88, 88. I don't want to write them all out. Let's just use them as they are. So if I go here and I look at the first 9, that's 4. That's 9, right? And then I mark off the next 9. There's 1 right in the middle. What is that? That's your median. And what is your median here? It would be 98 or Q2. You're right. Okay. Now, if I want to find Q1 or Q3, I do the same thing with the first half of the data or the second half of the data. Okay. So if I'm looking at these first, we said 9 numbers. What's 9 divided by 2? 4.5. So we look at 4 and 4. And right in the middle of those is this number right here, which is 90. So see if you can identify Q3. Okay, so 4 over, so here, here, and then 4 on the other side, we leave this one right here, 104, you're exactly right. Okay? That's it. I think we're done. Any questions online? All right. Thank you all for coming. Please take some candy.